Functions and graphs. We're going to look at this function, y is equal to x squared minus 2x minus 8. This is a quadratic function. It's quadratic because it has a term in x squared. It's not like a line, because the lines only had x's, or 3x's, or 4x's, but they never had anything like an x squared. Because it's a quadratic, it's going to turn once. This graph turns once this way at the bottom. You could equally have a graph that turns the other way from the, it might have a maximum point rather than a minimum. This is very much like the inside of a vase, maybe. And you have a little marble, and you drop the marble here, and it would roll all the way down, and eventually through friction and a bit of time, it would settle on the bottom. And that's what this inside of this vase is, or vase is, or whatever. Or bowl, or whatever. Now, it's an interesting point because there are a few interesting points about this graph. It brings a lot of the course together. If you were to look at the graph, you'd say, yeah, but actually, in addition to the shape of it, there's an interesting point here and an interesting point here. These 2 points are where the graph intersects or crosses the x-axis. So in many ways, we could say if that was y is 0, or let's say that was profit or loss, we could say we're making money here, and losing money anywhere here. Break even is just there. We don't make and we don't lose. That's exactly the crossover point. And those points are interesting on the graph. Now there's another interesting point as well if you look at it, and that's this point here, where the intersection here is with the y-axis. We say the y-axis is x is 0. There's no east or west here. We're saying just purely north-south. Where's the x-axis here now? And there's a fourth interesting point in this curve, and that's here. Probably the most interesting, really. Most of value to most people is just this one here, because that point there, 1 minus 9, it's where the marble stops. It's where everything stops. It's where the sort of it will just stay at rest. The slope isn't forcing it down. The marble won't roll east, and it won't roll west. It'll just stop there. It's like unemployment falling and then rising, or your health falling and rising after a regime you've got fit or better from a cold or whatever. You're getting worse and now you're getting better. Some turning point like that. So we can now see that the function in the graph here, a lot of things going to it. Nice, pretty picture. Nice, single chain like you would have, say, in something swinging like that in a chain, or with power lines between 2 poles, or electricity lines, a cable in some sort of shape like that. And 4 points of interest. So we'll stick around for those and we'll see what we can do with that graph. So the first thing we're asked to do is maybe draw the graph. They might give us values. And they might say, for this graph, find the values of fx by plugging in numbers. Now, we're used to doing this. We say, what's the value when f is 1? So if f is 1, everywhere we see x, we put in 1. So when f is 1, x squared will be 1 squared. 2x will be minus 2 times 1. Minus 8 is minus 8. So 1 minus 1 squared we do first, because that's part of PEMDAS or PEMDAS. 1 squared is 1. 2, 1 we multiply in, that's a 2 with the minus in front of it, and the minus 8. 1 minus 2 minus 8 is minus 9. Now remember that really, when they use this term y, or sometimes they use the term fx, there are only 2 things in the whole course. There's only 2 dimensions. You only have paper. So it's always x or y. So really, fx is really just another word for y. Or sometimes written fx, this sort of stuff. But it's really y we're talking about. So this f here is really y is equal to x squared minus 2x minus 8. Because when we draw the graph, it's the y-axis we're talking about. That's our function. So it's really y or fx. So we can draw all those points. And the point I got here when I got 1 was the point 1 minus 9. Why 1? Because 1 was the x value. And x became first. X is first, horizontal first, y second, 1 minus 9. That's my point. I can take another point, say 4. And we say, what happens when I put in 4? Well, I get 4 squared for that. Minus 2 times 4 minus 8, so that's 16 minus 8 minus 8, that's 0. So it looks like 4 naught is a point. And what I can do with all of that is I can then just draw those points. The 4 naught is a point, and I might get the minus 2 naught, or I might get this point. The 1 minus 9 I got. And when I've got all these points on my Cartesian graph, I then, as best I can, with a pencil or a pen, join those up in some sort of shape. Okay? Either with the, whatever curve or whatever you have, or bendy bit of rubber or whatever, or just by eye. Okay? So we then say, now's our graph, and we have that, and it looks like that. Okay, now start looking at the points of interest. Well, one of the points of interest fairly early on was this idea here of the intersecting points. So what are they? Well, the good thing about this now is that this is really an equation, this fella here. But even though we don't see it as much, I know it's boring, and it's so hidden away because we're so used to seeing the x-axis, we don't actually think it's a line. But it is a line. All the points here have a y of 0. 0, 0, 1, 0, 2, 0, 3, 0. Y is 0. So the equation of this is really y is 0. In other words, is y is equal to 0, x plus 0. The x value is 0, so y is 0. So effectively what we're saying is that there are times at this point here, A and B, that these points are both on the x-axis and on this curve, or both on the y equals 0 and on the y equal x squared minus 2x minus 8. So now we just actually plug that in. And we say, when is y equals fx, we only have an fx, is this equals 0? And x squared minus 2x minus 8. Now, in algebra, we would address that through factors. So we're not really doing it through graphs, but we're going to do this through factors. And we say, how would this become 0? Well, we're now going to look and see, how do we get the components that add up to this thing? X squared minus 2x minus 8 is 0. Now, x squared minus 2x minus 8 is 0. Well, what we would have done on the algebra side is we'd say, what are the numbers that multiply to give us 8? And we'd say 4 and 2. What are the numbers that give us x? X and x. But we want a minus 8. Well, it might be minus 4, plus 4, minus 2. But we want this one here to be a minus overall. So if we took a minus 4 and a plus 2, that would look promising in a way because we'd get the minus 8 here, and it would look like we get a minus 2 overall. We could prove that. Americans call this the FOIL method when they multiply. They say first, outside, inside, and last. And the first one is you take the two first ones, the first in each category, x by x, and that gives you x squared. Then you take the outsides, which is the x by 2, and that gives us 2x. Then you take the insides, and you say minus 4 by x is minus 4x. And then you say minus 4 by, the last ones then are outside and last, minus 4 by 2. 4 by 2 is 8. That's a minus 8. Now we would do much the same here. We would say x minus 4 by x plus 2. We would say let's do the x times x plus 2, and then minus 4 times x plus 2, which is exactly the same. X by x, x squared, x by 2, 2x, minus 4 by x, this, and minus 4 by that, 8. So that's our equation. But looking at that, these are the same types of terms. It's 2x and minus 4x. It's like 2 bananas and 4 bananas. It's like collecting them together. They're the same thing. So you may as well call that x squared minus 2x minus 8. And that works out. And that we want it equal to 0. And it looks like, at least, that that is the same as that. So we got it. We found that the factors of x squared minus 2x minus 8 are those two. So let's see, where does that leave us then? This says that the factors are x plus 2x minus 4. Now, we have to go one more step. And what we're saying here is that really we want this to be equal to 0. Why? Because we're interested in the y equal to 0. We're interested in the x-axis. So x squared minus 2x minus 8 is 0. And we simplified that says x minus 4 by x plus 2 is 0. The only way you can get something to be 0 when you multiply it is that one of these has to be 0. Either this is 0 times something, or this is 0 times something. So either x minus 4 is 0, or x plus 2 is 0. Now, if x minus 4 is 0, how would we solve that equation? How would we get rid of the minus 4 on that side? Add plus 4 to it. That would get rid of it and leave 4 on the other side. Basically, x is equal to 4. What would happen here? X plus 2 is naught. Well, if we said x plus 2 minus 2 is naught minus 2, the 2's would cancel, and we get x is equal to minus 2. X is equal to minus 2. So what this is saying is that there are 2 points, 2 values of x, 4 and minus 2, at which this stuff here goes to 0. The function y is 0. And if we look at that, we see that at x equals 4, which is here, and that x equals minus 2, which is here, that is indeed the case, where the function, this one, the quadratic, is actually sitting on the x-axis. So they're right. They're called roots. X equals 4 is a root, and x equals minus 2 is a root. To turn that into a factor, you have to make it equal to 0. So what they say here is that if x equals 4 is a root, then x minus 4 is 0. Because obviously if you say x minus 4 is 4 minus 4, x minus 4 is 0 because they'd cancel. Similarly, if you say x is equal to minus 2, well then x plus 2 is minus 2 plus 2. X plus 2 is 0. X plus 2 is 0. So these are called factors. And these are called roots. So the whole combination of roots and factors basically say that these are points x equals 4, where it crosses, that's the root, x minus 4 becomes the factor. So roots and factors are all intrinsically linked in this space here of this quadratic. As a quadratic, it will only ever turn once. The line didn't turn at all, but this will turn once. But let's say you did this question and you said, yeah, but that's all very fine. Sometimes in the exam I'm quite stressed and I can't always see it, and it's not always as easy as these numbers. What happens if I don't see the factors that simply? Where do I go then? Well, let's imagine that you didn't see the numbers, or it was more complicated. What we have is a formula that we have from the junior certificate, and it's still around, and it's still used a lot, to actually crack a quadratic. And what we need is it works for every quadratic of this form. It's important to write that equation out, because it basically says that it's mapped 1 to 1. So what we do is we draw this grid, and we say that in the general case we have A, B, and C, where A is the coefficient, the number before the x squared. And in this case, the number before the x squared is just 1. There's one of them. So we say A is 1. And we say B is 2. But we always have to be aware that the sign is also important. So this plus B is minus 2x. So that B is actually minus. And the C is equal to minus 8. So we can leave this table of data here to come back to. It's sort of our store. We've done that bit of work. The next thing is we look up the table, the formulae, or we might know it. And this says x is equal to minus b plus or minus the square root of b squared minus 4ac over 2a. Now, while that equation looks long, every single one of the numbers is known. We don't have to reinterpret it and find it out. We're just plugging in numbers here. So we measure one by one. We say, okay, x is minus b. Do it slowly. Minus b. Minus b is minus 2, so that's minus minus 2. Okay. Got a plus or minus, then we've got b squared. But b is minus 2. That's squared. We minus 4. We've got a. A would be 1, and the c would be minus 8. Okay, and that's all over 2 times a, and that's 2 times 1. And we just basically then say, let's take our time on this. Now, clearly, if we make a slip, they'll have to follow us in, and we lose a tiny percentage. But they'll have to follow us. But let's just do it slowly. Minus by minus makes that a plus. So x is plus 2. The plus or minus is there is useful. Now, the square root. Minus by minus is plus, so that's 2 by 2 is 4. With the plus, that makes that a 4. Minus, well, 4 by 1 is 4. By 8 is 32. Minus by minus, that's plus 32 over 2. So we're now up a bit. We've got made some expression on that. So here we have the numbers. We're getting close. We're using the formula, and we're getting somewhere with it. So we have, at the moment, 4 plus 32. But 4 plus 32 is 36. So actually, it turns out to be x equals, and we say plus 2, or 2, plus or minus the square root of 36 over 2. So there are two answers. We're now going to take the first one. The first one is x1, we might say the plus value. So we say 2 plus root 36 over 2. And the second one is 2 minus 36 over 2. Root 36 is, square root of 36 is 6. So that's 2 plus 6 over 2. And this is 2 minus 6 over 2. Now, when you're taking the square root of it, you don't have to go plus or minus again because you've done that. 2 plus 6 is 8 over 2. 2 minus 6 is minus 4 over 2. 8 over 2 is 4. And this is minus 2. It looks like we're getting the same answers. It looks like we're coming in on x, which was the starting point for all of this, the x value. X is equal to 4. X is equal to minus 2. Or if we wanted, x minus 4 is 0. X plus 2 is 0. So all we're saying there is that if we didn't spot it, if we didn't see the formula, if we couldn't sort of do it just there and then, and we're just a bit concerned about it, we use the sledgehammer, we use the minus b, because it's often necessary to do it. Sometimes it doesn't come out. And in complex numbers, you do need to use this. But we get 4 and minus 2. Again, we look and we say, here we have 0.4 and point minus 2. So we now move on and we say the next part. What happens when we intersect with the y-axis? So what I'd like you to do now is just write down the two equations that define that point there. What is magic about point C? What is happening there? What two equations are coming together at that point? Okay, returning to this. Y is equal to x squared minus 2x minus 8. Well, point C is certainly on the graph of the quadratic here, but it's also on this line here. Now, this is the y-axis, but what defines the y-axis? Well, let's look at the points. 0, 0 is on it. 0, minus 1, 0, minus 2, 0, 1, 0, 2. It looks like this isn't ever moving east or west. It's only ever moving north and south. So the east value is always 0. So it looks like another name for this is that x is always 0 here on this line. So if I were to draw a line of the points where all the points are equal to 0 for x, it would be the same. Just as this point here, 6, if I were to draw a line here, this is the x equals 6 line. Because this is 6 naught, 6 1, 6 2, 6 3, 6 4. Everything here is pretty boring. It's all 6. So this is the x equal to 0 line. So we've got two things coming together. X is 0 and this. So we just plug that in. And we say plug in f of 0 because we now know that x is 0 into this equation. So 0 squared minus 2 times 0 minus 8 is 0 minus 0 minus 8 is minus 8. xy is 0 minus 8. We know it's going to be 0. We come down here. That falls, we've minus 8 left. That's the point of intersection. So now we've intersected both graphs. Next one now is a particular point on a graph? So you're asked this question, is point 0.3 on this graph? Well, if you're asked to do that visually, I think you'd say clearly it's not. Okay? If you didn't have a graph available to you and you had to solve this algebraically, well, how would you do it? Well, you have an equation, remember, for this graph. You have a few times, we have it there a few times. And we know that the graph is x squared minus 2x minus 8. So let's plug in the value. And if we're asking for a point 0.3, we know that that's xy. Every point is xy. So let's see if it works. Let's try the point xy in the space x squared minus 2x minus 8. So let's try 0. 0 squared minus 2 times 0 minus 8 is minus 8. And we get the point 0 minus 8. Do we get the point 0.3? No, we get the point 0 minus 8. But maybe this is on it as well. No. The way it works is, because this is what we call a well-behaved function, as you move from left to right, for every x value, there's only one y value. X value, one y value. X value, one y value. So if the x value out here is 0 minus 8, it can't at the same time be 0.3. It just doesn't work like that. So if it's down here at 0.8, it can't be up here as well. The graph doesn't do anything fancy like this. Now, there are some fancy graphs that do that, but this isn't one of them. A quadratic will only turn once and will always move from left to right in a measured way, and for every single x, there's a single y. There's only one part in your course where that doesn't happen, where you've got two values for the same x, and that's when you've got a circle. But here, if this point isn't on the graph here, if you get a different value for x, it's not on the graph. So the next question you're asked then is, where on the graph here, where on this graph would the value of fx, or y, another term for it, when is fx greater than 0? Business people would say, if that was in that, when are we making profit? And when are we losing money? Well, this is the break-even where we've no money. Here we've money, here we owe money. Where's profit and where's loss? Where's break-even? I've paid off my debts, I don't have any, but I'm breaking even. Where's that magic line? And we can draw that line and we can say it's actually the same old x-axis. But at what points in the number line does it happen? Well, it looks like at this point here, if I go below here, back here, any value here looks like it's profitable. Any value here looks like it's profit. Any value here looks like it's loss. So I might shade the graph just like this. And I say, if I go to the left of 2, minus 2 here, over here. It's clear at this stage that f of x is above the 0 line. And similarly here at 4, it's above the 0 line. Whereas here it's, well, it's pretty bleak. It's like midwinter, it's lots of darkness. Here, bit of sunshine, great. 21st of March, 21st of September, it all starts swinging around or whatever. But you see the various cycle of daylight or cycle of whatever. You can see here that that's positive, this is negative. So what they're saying is that f of x, really we mean y, because we only have two x's, y or f of x and x. F of x is greater than 0 whenever x is less than minus 2. So below minus 2, we're sorted. Also above 4, when x is above 4, f of x is greater than 0. And between the two, the negative sides, is here we've got f of x is less than 0 in this space here. So how do we draw that then? Well, how do we explain that algebraically? We say y is fx has positive values when x is greater than 4 and x is less than minus 2. This section here, greater than 4, this section here. But sometimes they want that as a single expression, and you have it as 2. You have this one, and you have this one. You've only one x, and you'd like to put them in order. You'd like it as a single line. Now, so you've got this equation here, and this equation here, and you'd like to join them. Well, the logical way for us to join something on paper is to put the smallest number first, the minus 2. And the 4 here. That before that, because that's the way the number line would suggest it would go. The minus 2 is left of the 4. Now let's look at the relationship we have. We've got x is greater than 4, and that's okay. That means that this part of the equation we've sort of copied pretty much. But this one here is messy because we only want to have one x. But if you go from x to minus 2, look at what happens. As you travel from x to minus 2, you hit the pointy bit of that symbol first. So when I go from x to minus 2, I should hit the pointy bit first. That way. Or that way. If x is less than minus 2, it's x is minus 2 is greater than x. So in the end, I just get one equation. Minus 2 is greater than x is greater than 4. Does that make sense? Well, if minus 2 is greater than x, that means that x is here. And that means that it is indeed positive. Similarly, if x is greater than 4, that means it's here, it's positive. So in both of these sides, it's positive. This is an interesting question they give you, and they say, where does the graph, the lines, intersect a graph twice? Now this is a bit tricky. What do they mean by that? Sure, every line intersects twice, wouldn't it? Even if it was a bit crooked or something, not crooked, if it was at an angle. Like if the line was like that, wouldn't it cross twice? Or here, wouldn't it cross twice? Or here? But what they do is they say, okay, let's imagine that the lines are horizontal. Which lines cross this twice? So what I'm going to do is I'm going to put them on a map like this. And I say, I've drawn a whole load of series of horizontal lines now. There's a horizontal line. There's another one, another one. And these are the ones that's specified in your syllabus, the horizontal ones. But at some point here, you stop crossing twice. And here, you're not crossing at all. Here, you're sort of crossing twice, and then here, nothing. But you get the impression that at some point, pretty important point here, this point here, 1 minus 9, you're sort of just on the verge. It's the place when you're just touching it once. It's the tangent. It's the perfect sort of finishing point, just before you let go. Here, you'd have two values, minus 8 and another. And way up here, the values are getting far apart, etc., etc., etc. So how do you do that? Well, what they say is they say that every line, this was y equals 0, remember the x-axis, y1, y4, y to minus 2, y to minus 12. How do you find out what this line is? How do we get that? How do we get this, this magical point where it just touches it once? Is there an interesting point here? How do we get that? Well, it's this point. It's the minimum point. The minimum point is defined as the only point where the marble will stop rolling. The only point where the slope is such that it won't cause it to roll forward or roll back. The slope has to be 0. The slope here is quite positive, very severe here, quite gentle here, gentler here, negative here, quite negative here. Here, 0. How do we find out where the slope of a curve is 0? How do we find out anything about the slope of a curve? Well, let's look at the actual curve itself. The curve is given as y is equal to x squared minus 2x minus 8. That's for every x and y value. How do we define the slope? What's another word for the slope? dy dx, isn't it? So what is dy dx of that curve? X squared becomes 2x. The minus 2x becomes minus 2, and that falls out, doesn't it? So the dy dx, the slope at any point in the whole curve, is 2x minus 2 for every point. Well, what particular point are we most interested in? When that slope is 0. And when is 2x minus 2 equal to 0? Well, when 2x equals 2, when you take the 2 across. And when is 2x equal to 2? When x is equal to 1. So when x is equal to 1, we're saying that when x is 1, here the slope is 0. Now what's the point when x is 1? Well, when x is 1, the function is here. So we say x is 1. So we say y is equal to 1 squared minus 2 times 1 minus 8. 1 minus 2 minus 8. 1 minus 2 is minus 1 is minus 9. So really what we're saying is the point xy of 1 minus 9 is the point on the function, on the quadratic, where the slope of the function is 0. This is the only point where dy dx is 0, where m is that, or tan theta if you want it. It's the only point where it's actually horizontal, the only point where the marble won't roll. And what line is that? Well, it looks like the y value is given by minus 9. And what line touches that must have a y of minus 9. So it must be 0 minus 9, 1 minus 9, 2 minus 9, y is equal to minus 9. Or, answer is y is equal to minus 9. K greater than minus 9 says that once you go above minus 9, you're back to cutting the function twice. At 9, you cut it once. If you go below, you don't cut it at all. Actually, if you put in the calculations, they turn out to give you a square root of a minus number, which is a complex number, which we could come back to, but it doesn't do it in any real sense. It doesn't cut that. So that's the turning point. The turning point, how did we get it? We got f of x is equal to that. And f dash x. F dash x is another way of writing dy dx. When all of this calculus was coming about, there were a couple of very bright people around in the Middle Ages. Leonardo da Vinci was one and Leibniz was another. Leonardo da Vinci was very gone on this one and Leibniz was gone on the other. And they just had two different things that discovered calculus or represented calculus much in the same way. But calculus has been around a long time. What is calculus? It's dy dx. In other words, it's y over x. It's something per something. Miles per hour. is the dy dx of distance. Acceleration, going from 20 to 30 kilometers an hour, is the change in speed. Anything that's a change of per something is dy dx. The rate of unemployment per 1,000. This per unit of. Calories lost per whatever. It's all dy dx stuff. It's all slope stuff. How many steps east do I go for every step north? So there's their dy dx. Remember that when we get the slope equal to 1, or the value of x saying the slope is 1, slope is 0, sorry, when the f dash is 0, that doesn't mean that the function is 0. It just means that the slope is 0. So if we look at it here, we can see here that at this point here, on 1 minus 9, the graph is saying that the slope is horizontal. The marble will not roll. Stay at the bottom of the vase. The slope is 0. If you move out here, the slope has changed. Here, the marble will quickly lash back, and here it'll go forward. So at every point on the graph, we do have a slope. And it's always defined by dy dx is 2x minus 2. But it depends on the x value. So at this point, when x is 1, 2 times 1 minus 2 is 0, and that's why the slope is 0. But if I chose a point here, for example, let's say this point here, 3 minus 5, what would the slope there be? Well, the values would be x and y, 3 minus 5. I could draw it if I wanted quite neatly, if I took the time. And you can see it's quite a bit of a slope there. It's moving quite quickly because as I move out and move up, it's sort of, for every step across, it seems to be sort of going up 4 steps here. It's quite fast. That's quite high. It's quite a high ladder. It's more than 45 degrees. It's more than 1 in 1. Looks like it's 4 in 1. I do that again. And I say, here I go from, it looks like again it's 4 in 1 as my tangent. But how would I get that actually? Well, the point is 3 minus 5, so that's 3 minus 5. But dy dx was given in general as 2x minus 2. Well, 2x minus 2, that's x and that's y. X is 2 times 3 minus 2. 2 times 3 is 6, minus 2 is 4. It looks like the slope at the point 3, 5 is, not only is it 4, but it's plus 4. It's up 4 for every one out. So that's how we manage slope. Very often they'll ask you, when you've drawn the graph, where is the slope positive? Well, here you have your graph, and you know that at this particular magic point here where the marble has stopped, the slope is 0. Up here, the slope is positive. Remember that positive means that as you go east, you're going north. That's positive. Whereas if you're going east and at the same time then going south, that's negative. That's just convention. Okay? So really what we're saying is that that's positive. It's 0 here, positive, 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 positive. Here, negative, 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 just about, and then 0. So the question is, where is the slope greater than or equal to 0? You say it's equal to 0 here. Outside here, it's over to the right. And that's all. They say, where on the graph do you find a point with a given slope? Here you've got your fx, and here you've got your dy dx. But you want the slope to be equal to 4. You're asked in the exam, when is the slope equal to 4? Well, you can imagine that you'd be a long time doing this with a sort of a, compass set and, all the various angles and stuff to work out that. But could we do it? Well, we know that at every single possible time that we have a function now that says y is equal to x squared minus 2x minus 8, but the dy dx, or f dash x if we want to call it that, is 2x minus 2. And they're saying, when is that equal to 4? So when is 2x minus 2 equal to 4? When 2x minus 2 plus 2 is that. When 2x is equal to 6, when x is equal to 3. So I now go to the point 3, and I say, at the point 3, the slope of this graph is 4. 4 to 1. Whatever way I do that, 4 to 1. But what is that point? Well, I can find the point by just plugging in the numbers into the thing. Because I know that the function is always called f of x is equal to x squared minus 2x minus 3. Or sorry, minus 8, isn't it? So I say 3 squared minus 2 times 3 minus 8. 9 minus 6 minus 8. 3 minus 8 is minus 5. So 3 minus 5. So now I found the point at which the slope is 4. Just as before I found the point where the slope was 0. I could have found the point where the slope was minus 1 or minus 15 or anything just by plugging in the numbers. So dy dx is 4 at that point. Why? Because dy dx is 2x minus 2. X is 3. 2 times 3 minus 2. 6 minus 2 is 4. If we wanted to look at it graphically, we could take the tangent, and we actually see that this point here, 2 minus 9, is on this curve, and 3 minus 5. And it actually goes 4 up for every one across. So in that case, you are given the point of 3 minus 5, and you're asked to find the slope, and you can do that. Now, what's left? What's left on the line is very few things. They say, okay, now you can do all the tangents. Let's see what they give you. They might say, find the tangent now. And by tangent, they mean give us the equation. The equation of the line at the point where the slope is a certain value. So imagine that here you are in this question, and they're saying, any chance you can get the equation of that line for us there, please? And this is where sometimes in the exam you've got to sit back and say, okay, this looks like a few steps. We've got to get the equation of this line. Okay. Well, that means where you get the line. You've got to get the slope of the line. To get the slope of the line, we've got to find, and it's a tangent. That means we must get the slope of the line at that point. But the slope of the line at that point, the red line, is the same as the slope of the function at that point. That's what makes it a tangent. Because if it wasn't, it would cut the curve or miss it. So this point here, the slope of this is the slope of this line. They have the same, it's 4, whether it's the line or the curve. So I reckon I can get the point by actually working out the slope of this function. So if I say x squared minus 2x minus 8 is f of x, dy dx is basically 2x minus 2. And if that has to be equal to 4, that's 2x is equal to 6, x is 3. I can now identify the point. I can identify the point 3. Well, that's not bad. I know that at point 3, I can find out that that's where the slope is, that's where the tangent is. But I also know from the graphs that if I know the x value, that x is 3, and I know what's on the function here, then all I have to do is stick in the value, and I get y is equal to 3 squared minus 2 times 3 minus 8 to find the point. And that, the last time I did it, was 9 minus 6 minus 8, 3 minus 8 minus 5 was the answer. So now I have the point 3 minus 5. So now it becomes a fairly straightforward line question. Given a point, given the slope, what have I got? I've got two things. All I ever needed to draw a line. The point was 3 minus 5, and the slope, m, was 4. There must be an equation for that. Y minus y1 is m into x minus x1, or something like that. I have x1, I have y1, I have m. I should be able to do it. So let's go and do that then. I look up the tables, I find the equation, I plug in the numbers, and I get that the line is given by 4x minus y is 17. I do a bit of tidying up, and I get y is equal to 4x minus 17. Now, y is equal to 4x minus 17. Y is equal to 4x minus 17 is the equation of the line, which is great. That's what I was asked to do. I should stop then. But I'll just look at one thing. What's dy dx of it? What's dy dx of that? 4. And that should give us some sort of comfort, because that's where we started the whole thing for. The slope of the line is the slope of the other. Very close now to the end. Intersection of two functions. This is where they ask you to draw two things on the same graph, one function and then another, and they say, would you find out where the two functions cross? Now, they have promised, and they've specified in the syllabus, that if one function is quadratic, the other definitely will be linear. So you won't have two quadratics. It wouldn't faze you even if you had two quadratics. It just happens that that's the way they define the syllabus. So we're going to look at these two, gx and fx. Remember that gx is just another y, because you only have y and x. We're just using the same graph. Find out where they cross, solve the equation. So basically what we're trying to do here is we're trying to imagine a situation where you've got the same fx, this blue line here, fx, but you've got a gx here, a red line, and they're going to cross. So that's the territory that we're in now in this question. So how do we do that? Intersection of two functions. Well, the first thing we should do is draw the function. So they might say gx is equal to minus x minus 2. We haven't drawn it, so we say let x be equal to 0. What's y? So gx is another word for y, is minus x minus 2. So if x is 0, minus 0 minus 2, y would be equal to minus 2. If x was 2 minus 2 would be minus 4. We have 2 points, 0 minus 2, 2 minus 4. They're just 2 points. 0 minus 2, 2 minus 4. It shows it doesn't matter which points you take. We might have chosen this one and this one, or any other set of points. We'll get the same graph for gx. So we can draw it. Checking the process with respect to the other function, where would they cross? Again, we're going to draw these, and we're going to say, where do these things cross? Well, how do we find out what is happening at this magic point A and point B? In a sentence, try to write down what is happening at point A and point B. What's really special about A and B that's not true about all the other points in that whole plane? What's the one thing that's happening in A and B that's not happening anywhere else? Well, the answer is that point A is on fx, and it's also on gx. So it's on both. So in other words, that this equation here is also this equation here. So let's see how we can do that. We're saying that if the two equations are the same, we're saying that f of x is equal to x squared minus 2x minus 8. And g of x, we had, what do we call g of x? Minus x minus 2, was it? Minus x minus 2. If we're going to find out where the two are the same, fx must be made equal to gx. So in other words, this part, x squared minus 2x minus 8 must be made equal to this part. We can join the bits over. The x squared stays. The minus x comes over. It becomes plus. It becomes minus x. And the minus 2 comes over. X squared minus x minus 6 is naught. So x squared minus 6x minus 6 is naught is what we're left with. Can we solve that? It's a quadratic. We can say it's x minus 3 by x plus 2 if we were spotting the factors. And the FOIL method would say that's right. So either x minus 3 is naught, x plus 2 is naught. Or x is 3, or x is minus 2. If we didn't see it that way, we could have used the minus b and solved it. But let's assume that we found that x is 3 and x is minus 2. What do we mean that x is 3 and x is minus 2? What we're saying is that when x is 3 here, that x value gives you the same value for the fx curve as it does for the gx. When it's minus 2, it gives you the same value for the fx and the gx. So let's look at that. What happens when x is 3? We get 3 squared minus 2 times 3 minus 8. Here we get minus 3 minus 2. That's 9 minus 6 minus 8, which is minus 5, and that's minus 5. And that's saying that at the point x is 3, y is minus 5, 3 minus 5 and 3 minus 5 are on both gx and fx. 3 minus 5 is where they cross. What about x is 2, or minus 2 is the other answer we got. We get minus 2 squared minus 2 times minus 2 minus 8. 4 minus by minus is plus, minus 8 is naught. Here we get minus 2. Well, it's minus 2, remember, because it's minus x minus 2. 2 minus 2 is naught. Looks like we end up with minus 2 naught here, minus 2 naught here. That this point is on gx, this is on fx, but it's the same point. This point is on both. So we have found the intersection of the two curves. Visually, they ask us, when is fx greater than gx? Here we've got fx, the blue, and here we've got gx in the red. And there's this period here between these 2 points where gx reigns supreme. It's higher value than the others, whereas here fx is taking over. So fx is greater here and here, but not here. So in other words, fx is greater than gx when? Well, from about this point here, when x is greater than 3. Here, fx is once again greater, higher, when x is less than minus 2. And here's the opposite way around. So how do we join those two again? We say fx is greater than gx. Here, when x is greater than 3 and x is less than minus 2. But we probably would like to do that as one big equation. On the number line, minus 2 comes first and 3 comes second. And we'll put x in the middle. X and 3 are associated with a greater than. X and minus 2, to get from one to the other, on this occasion you hit the pointy bit first, so you should hit the pointy bit first going back. So minus 2 is greater than x is greater than 3. So if minus 2 is greater than x, it means x is down here, then it's all positive. Once minus 2 ceases to be greater than x, it doesn't hold. second last topic. A graph of an inverse function. On your program, they can ask you to draw a graph like that. Y is equal to 1 over x plus 2. No different to any other graph. You say when x is 0, what's y? When x is 1, what's y? So if x is 0, y is 1 over 0 plus 2, y would be a half. When x is 1, y is a third. So 0 a half, 1 a third, and you can draw the graph like that. For example, if x was minus 1, y would be 1 over minus 1 plus 2. That would be 1 over 1, which would be 1. So it would bring you there. And we can draw the graph, and similarly on this side. It's just a fancy graph. So we can plot the values, and we say, what about f0, f2, f1, or f minus 1? We note that f of x is not defined at x equals minus 2. If we were to stick in minus 2 here, we'd get f of x is equal to 1 over minus 2 plus 2, which would be 1 over 0. And that's not defined. And you can see here that in this space at minus 2, really the graph, the red line doesn't touch it because it's going crazy. It's going to millions here and minus millions here. Very last. Other types of graphs and variants. There are graphs on your program that are not quadratic and they're not smooth sine waves. You'll see them on hospital programs. You've got a heartbeat, a blip. You'll see it in music recordings where you see the frequency coming through, etc. And there's a repeated pattern. When the pattern goes dead, generally the patient doesn't get on too well in the program after that, or whatever. Here's the graph they give you. It's a sawtooth. It could be any shape. But the one thing that will happen is it will repeat itself. So you've got to find the period, the pattern in it, like the wallpaper pattern. And you can do it from starting anywhere. In this particular case, I'm going to start with this dot here. And I'm going to say, I'm going to take that as a pattern for my wallpaper or whatever, that shape there, between those 2 points here. Somebody else might have decided, I'll just take it from here to where it crosses again on the way up. They might have gone from 0 to 10. Another person might have taken the whole thing from here. There's no right answer. You just pick any one of them. I happen to pick the blue one here as my pattern, my basic pattern. Now, I'm asked to do then is to find out what the gap is. This is 0.6 and this is 16. And 16 minus 6 is 10. This is repeating every 10. If somebody had done that in the green, they'd have gone from 8 to 18, which would be 10. Or if somebody had gone from here to where it joins again, it'd be 0 to 10. They'd get the period as 10. Everybody would. Then they say, well, what about the range? What's this spike? And there's a fancier way of writing that. It's f colon x equals fx. It's just a nice way of writing it, but it's just a y, really. Y is x, because that's the y, the vertical, and that's the x. So what's the highest value? When you just look at the tables, and this point here is 3, and this point here is minus 1. So 3 and minus 1 are the two gaps. And that's the range, from minus 1 to 3, or a range of 4. Now, what can they ask you to do? Well, they can say, how quickly does the pattern repeat itself? 10. What's its range? Minus 1 to 3, which we read from the graph. And then it says, find F4 for me, and find F84. Well, F4 shouldn't be too hard because it's here. So you go to the graph and you say 4, 1, 2, looks like it's there. It looks like F of 4 is 2. How do I get 84? Well, 84 is a million miles away here. I'm not doing that. I'm not going to spend the rest of my day doing this. It's just too long. Life isn't worth it. But what we're saying here is a pattern here of 10. So every 10 it repeats itself. So f of 4 is the same as f of 14. And actually, f of 24, and f of 34, and f of 44. So if I were to draw that, it looks like f of 4 is f of 14, 24, 34. It must be 84. So all I have to do is find out how many periods are there between this and 84. Well, 84, given that they're 10 long, is 8.4. But I don't talk about, breaking it up. They must be integer values. So really what I'm saying is it's 8. It's truncating. 8.4 is 8. So I'm going to say it's 8 plus, it's the value of 4 plus 8 other ones. So f of 4 is the same as f of 84. That must be 2. Thank you very much. See you tomorrow. You're very good. That's a long day for you. Thanks a million. You must be wrecked. And see you tomorrow. We do 3 more sessions. Half the leaving cert covered. And you don't have to worry about maths for a while. Okay? Thanks a million. Safe home.